Hi. Well, today this webcast is going to be about data-driven measurements, and often we're required to make measurements of a whole variety of different things, and sometimes it helps to think carefully about why you're doing it, which sounds like an obvious thing to do, but it's very common just to be told to go and do a measurement and rush off and do it, and then later realise that you could have done it this way, it might have been better, or the data ends up being used in a way you didn't expect. So what I like to try and do is think through, when you're asked to do a measurement, what's that resulting data or information going to be used for in the end, and how are people going to consume that? And when you start to think about what that end product looks like, and that might be the end graph it looks like, or a table of results it ends up in, that allows you to structure your measurements in a way that all aims towards that. So today we're going to talk a little bit about this idea of data-driven measurement. And part of that is, like I said, determining the reason for why you're doing that measurement. We'll talk about a few examples of that. And then try to develop an expectation of the kind of data you're going to get out, and then think about how you then handle that data and manipulate it to get the actual end product that you want, the information you want, or the actual result that you want, and whether that's for yourself as an internal investigation or whatever, or whether it's going out to a third party, an end client, or being used further on past that. So why do we do measurements? Well, typically we're trying to obviously measure something, probably about the physical world, but sometimes they are actually measurements to understand the underlying process and investigate, say, a root cause investigation of a failure. What actually happened? And you're very then concerned with understanding physically what happened. Other types of measurements might be compliance-driven, where it's actually a risk reduction process, where somebody said, well, just go and measure it to this standard so that we can tick a box to make sure that we're not doing anything bad. The physics of what's going on underneath probably aren't as relevant as making sure you've done everything in compliance with the standard, whether that makes physical sense at the time or not. So they're slightly different requirements. So some examples of a sort of more of a physics-driven or process-driven example of a measurement, like I said, root cause analysis is a classic. You might have, a tram with some failing component. You want to measure on that tram, understanding what environment is exposed to, when those conditions arise, are they anywhere near the design envelope for that thing, or then you might be then using that data actually to feed into another model, like a digital twin of that, and then you're saying, well, with this data, we'll feed it into the model and we'll come up with information that we can compare against the design envelope. You might be measuring structural performance of something like a bridge, and once again that's more with the verification digital twin kind of idea. So what are the mode shapes of this bridge? How does it respond to wind loading? Does that line up with what we expected? And then you've got cases where you're doing, say, acceptance testing on a system. The system's supposed to have some sort of physical performance. It could be an antenna, it could be a train bogie, and you're measuring these parameters and you're comparing it to a requirement in a specification, and that's important for verifying that the system does what it says it should do. And then, as I mentioned earlier, you've got that legislative or compliance-based measurement, where in that case the requirement is to measure to the standard, and the importance there is to make sure you measure to the standard. The applicability of the standard is a separate issue, and sometimes you end up measuring to a non-applicable standard or whatever, but that's at least if you understand that up front, you can be clear about what you're doing. When you do a measurement, you might say, well, we don't know what the data is, we haven't measured it yet, but you know that it's not stupidly large or stupidly small, etc. So you might, if you're measuring, for instance, you're measuring, say, structural vibration on a support for a machine, you've got some references like ISO standards to say what typical machines should look like. And, you say, well, okay, it's a big machine, so it's probably doing, 5 to 7 millimeters per second, probably at, 25 hertz or something, or, 12 hertz. And that gives you a ballpark to what you're thinking about. You're not talking about measuring 7 microns per second. And so when you design what equipment you need to take and what you're going to measure and what matters, you've got an expectation for what that data looks like. If, on the other hand, you are measuring, say, a silicon fab facility, then 7 microns per second does become important, and you select gear and processing in a different way for that. So you've got an expectation about what your data might look like, and you may have multiple channels of things. You might have some vibration, you might have some temperature, you might have voltage, supply, and you might have a process command, right? And all these data streams are going to look a bit different. Your vibration is going to look pretty shaky, right? And might have some harmonic component, but sort of some random stuff. But it's going to be varying quite quickly with time, for instance. Temperature, probably not. Temperature is probably pretty steady. Doesn't do anything very exciting. Your voltage is going to be the output from the supply. So that's going to be a nice steady state sinusoidal thing. And probably going to be at 50 hertz. You know that. So that's quite a defined signal. And your process commands, who knows what they are, could be from the PLC or whatever. So you might have a sort of switching kind of mode where you're switching between modes. So it's that sort of signal. And this might be 24 volts, 0 to 24 volts perhaps. This is going to be 50 hertz, depending if it's 3-phase or whatever, it's 415 volts. Temperatures, it's not minus 300 to plus 1,000. It might be 20 to 80 maybe, I don't know. It depends what it is. And vibration, like I said, you might be able to guess that it's approximately, say, 7 millimeters a second-ish, right? So you've got to have an idea about what size these signals are and what content they've got. So the vibration, it's not going at megahertz, but it's not going at 0.1 of a hertz either. We're probably expecting this to be in the 10 to 1,000 hertz range. The temperature, it's almost DC, but not quite, but it probably varies on the range of several seconds, Like I said, the voltage is pretty well defined, 50 hertz at a certain amplitude, and this process thing is going to be a digital switch. We don't really care, perhaps, about capturing that edge to the nanosecond. If we capture this transition to within these time contents, so a millisecond would be plenty, right? So already we've built up a picture of what our data might look like, and by doing that before you do the measurement, it definitely helps with the hardware selection and the measurement setup, but it also helps with thinking about how you're going to process that data. What's a meaningful thing to talk about? Is it meaningful to show somebody a time history of the 3-phase supply in like 100 figures at the back of the report? Probably not. You just want to say that it was that, and it was sinusoidal and the harmonic distortion was whatever. So what we're going to go on to talking about next is then, once you've got these signals, how do you start to think about how you process them to pull out more information? So we've talked about what the expectation of our signals will look like. And now I want to talk a bit about the idea of how we reduce those signals to increase the amount of information in them, the sort of idea of information density. So, which is a quite useful concept. If you think about, let's say we've got a random signal, right? Whatever it is. We go out and we collect 100,000 points of data. Now, one way to describe that signal is to draw that out, or recite out 100,000 numbers. But that's not a very convenient way to talk about that signal, and it doesn't have a lot of information in it. So what we want to do is reduce this down to something that captures more information. And obviously you've got tools like statistics to do that. So taking these 100,000 points, you could average them all and you can come up with a mean value, whatever that is, I don't know, 87, which tells you what the signal mostly is, most of the time, which immediately gives you a lot more information than just a big string of numbers. You know, you can tell people, oh, it's roughly 87, right? But you can also think about having a distribution that describes this signal, right? So some of the values are you've got a few values that are small, most of the values are around 87 and a few values that are much bigger, right? And everyone's seen a probability distribution before. So by talking about the mean and then talking about a standard deviation either side of that describing this whole signal, these 100,000 points with these two values, the mean and the standard deviation, you've now given a lot more information. You said that not only is it this most of the time, but I'm pretty confident that 68% of the data or whatever is within these bounds. And then you can, say things like, well, 99% of it is within 3 standard deviations. And that gives you even more confidence about the data. So if you're measuring something to determine if it's a problem, like you might know that if this signal gets to this level, bad things happen, but most of the time it's down here. But you can say, well, there's a 97% chance that that signal will go above that level, and that's far more useful than just giving somebody 100,000 numbers and going, well, I didn't see any big values, I reckon it's okay. So depending on the purpose of what you're going to use that for, you're thinking about what data am I going to present in the end, and in this case, the mean and the standard deviation, and actually the actual bit of information you're going to present really is the percentage chance that this signal is a problem. That's the story you're going to tell at the end, and then there's levels back from that. So that's one way of reducing data, and that works really well for a random signal like that. There's other things you can do. You could talk about taking a spectrum of data. So once again, you've got a signal. Maybe it's a little bit more harmonic, right? And once again, this could have hundreds of thousands of points in it, right? And you can describe that with the mean and the variance and all the rest of it, but you might want to know what's the primary frequency at which things happen in this, right? Is it something that varies at a fast rate or a slow rate? And so you take a spectrum. Instead of having 100,000 points, you would reduce this down to, say, 1,000 or so points, and you might have a spectrum that looks like this. Whatever this is, 1,000 hertz, whatever. So you've taken all this data and you've reduced that down in size to a much smaller data set, but also you've now got an idea about this line here is going to be effectively your mean at each frequency bin. So if we pick a frequency bin here, whatever that is, 32 hertz, right? We've got an estimate for the energy in there, and by implication, there's also really a standard deviation around. So it says that your mean value is this in that, and then if you do some extra sums, you can find out plus or minus what, yeah? But it also tells you that most of the energy is happening here and here, and because these things, you can then relate these things to some other physical process. So if this was vibration in an office building, and this is 25 hertz, that's all the plant, the air conditioning and pumps and whatever, all rotating away, and you can then correlate that to a physical thing. And once again, you've got to think about what are you going to show the end consumer of this information. Showing them the time history is probably the most obtuse. Showing the spectrum is also not that informative for the uninformed consumer of stuff. What you really want to say basically is, this demonstrates that the chiller on the roof is what's causing the disturbance. And when we measured it after doing some magic intervention, this number went down, so dollars well spent. And so if that's what you're thinking about at the beginning of the measurement process, you're always aiming towards that the nugget of information that you hand across to the end consumer of that. Right? The other thing you could do, you might have two processes. I don't know. There's one process. Here's another process. Right? Both kind of random. Process A, process B. And you want to find, are those two things related? So once again, you can describe both signals and you can talk about what they are, but showing if there's some sort of correlation between them might be what you want to find, what you want to demonstrate. So you can plot all these points out and you get a big collection of data. And you can fit some sort of line through it, okay? And with the right maths, that line is the line that has the least error between all these points. And you can now describe these relationship by the equation of that line, which might be some sort of quadratic or something. So you've got what are we going to have? A times b squared plus b times b plus c or something. So we've reduced down this big cloud of data points to these coefficients, A, B, and C, and that describes the input-output relationship for this particular process. Now, you can also do that in the frequency domain too, by measuring transfer functions, which is a bit more complicated, but same sort of idea. Yeah, so we've been chatting about thinking about your data, expecting what your data is going to look like, coming up with data processing tools that increase the information density in that data. So that's almost like a little pipeline of process, and that's kind of what it is. So you've got your raw data coming in the top, and then we're going to apply some reduction to that. So we've got data reduction going on here. Now, that data reduction phase, you can do that multiple times. That can be an iterative process, right? You could go around that loop until you've pulled out exactly what you want. And that might be a combination of data filtering, taking spectra, doing kurtosis analysis, doing correlation analysis, fitting to models, but it's this pipeline, and at the bottom of this pipeline, eventually pops out this little nugget of information that you can actually show somebody, Let's not make that box a bit bigger. There we go. Should have thought about that beforehand. So this information, like I said, always at the beginning you're thinking, well, what's this going to look like? Often when I'm thinking about this stuff, I'll sketch out what I think the final graph's going to look like. And if it's a transfer function between things, I'm saying, well, look, we want to show that it's pretty much a unity function, but there's a resonance here, and then it rolls off. So that's what I'm imagining my graph's going to look like. Or you might be thinking, all you want to show them is a distribution of stuff, and that their criteria is outside of 3 standard deviations. So by thinking about these things first, you can plan what this stuff has to be and sequence this to get the right answer. So with, we have a platform called DataFlex, which is built in this way, and the idea being that at the front end, you've got a very flexible data acquisition system that can handle a varying number of channels, lots of different rates, different kinds of data types. And then because of the way the software is designed inside, you can build up this data pipeline process and bring in modules and take modules out and come up with basically that refined bit of data. So we've done things where perhaps you might have a specification that you've got to meet, which is quite non-standard and quite bespoke, and written in such a way that just off-the-shelf data acquisition is challenged by that. But what we were able to do was specifically design this pipeline that addressed exactly just that need. And then once we had that information pulled out from the signals, we could then set up automated alerting and reporting based on those specific criteria, which were not your standard RMS vibration levels or overall sums or whatever. It was quite a specific thing. So, and in another case, we had a system where it was an investigation into the behaviour of a large antenna, and so we had to collate a lot of data and then pull that down to a few key metrics that showed whether it was in compliance with what it was designed to do or not. And although there was a lot of data was involved in that and quite an extensive amount of measurement, the focus was always on, well, how do we get that metric so that we can compare it against this requirement and show that they're not in alignment. So what we ended up with was a sort of curve of performance, a whole bunch of different performance spots that we measured versus, there was one sort of input parameter here, and this was our performance, and we knew that it had to meet this line, and we could show that, okay, out above this level here, we don't get performance, or you're quite likely to have outside of the required performance on that system. But the whole focus was about coming up with this sort of plot, with this sort of trend line to say, yep, above this value, the system's not performing as it should. So in summary, by thinking about your measurements as data-driven measurements, you can plan out the pipeline of data processing that's going to happen between the raw data you collect and that final bit of information that you hand over to the end user. And by being aware of what you expect at each of those steps, you can make informed choices about how you design that pipeline. Now, there's a lot more we could talk about in terms of various processing techniques and how you structure different kinds of measurements to obtain different kinds of data sets. I'm sure we'll do some videos on that in the future, but the main point of today was just to introduce that idea of output first and then let that inform your decisions all the way through. So if you've got a good reason for doing the measurement and you're clear about what you want to come out the other end, you're more likely to get the data you want and not have that terrifying situation of getting back after 3 days on site and looking at the data and going, oh, that's not what I needed at all, which is not a good feeling, and I'm sure some of us, if not all of us, have been there at least once. All right, so thanks for your time today. We're opened up for questions, as far as I know. We'll see what's come in on the chat, and we'll hand back to Maurizio.
All right, well, thanks to Mike for the talk today. It's great. So, first of all, just want to introduce Peter, who you can't see, but he's running our production in the background. So yes, thank you, Peter.
Thank you, Maurizio. Yes.
All right. So for the reason also to introduce Peter is I want to check if there were any Q&As at this stage.
Nothing in the chat at the moment, Maurizio, but if something pops up, I'll let you know.
Okay, go. That's good. Anyway, we'll take the time for Mike to introduce the next episode in this webcast series on data and measurement.
Yeah, so obviously what we were just talking about was all about trying to decide what your data looks like up front. The next topic we're going to cover is more to do with bandwidth and sample rate, and there's obviously the traditional way of looking at that, the boring old, here's the Nyquist frequency, here's some aliasing. But when you have a look at transients in signals, you do get some strange effects. So I'm going to talk specifically about analyzing transients, using Fourier analysis to do that, when it's a good and when it's a bad idea, and comparing that to time-domain methods. So that one we're putting together shortly, it'll be a few weeks before we schedule that.
Yeah, we'll advertise it, of course, as always. So watch this space, as they say. Okay, thanks, Mike. Peter, I guess we don't have Q&A now, but...
No questions. So Mike must have explained everything perfectly.
Absolutely. As always, by the way.
Unlikely.
Well, let's go likely. But anyway, obviously, if you have any questions, you can reach out to us via our website, resonatsystems.com.au, or email info@resonatsystems.com.au. You can find us easily. on the web. The video, as I said earlier, will be uploaded on the YouTube channels and linked up. And so, well, thanks to the one that joined us live today, and of course, thank you to those ones that will watch this in playback later. Okay.
Yeah.
Great.
Thanks, guys.
Thank you.
See you next time.
See you next time.